Hi everyone, Jessica Stockdale here, and I'm back with another and indeed our final Math152 video lecture. So in the last lecture you learnt about Taylor series and Maclaurin series, what these are and how we can use them, and today we're going to finish off the course with I think anyway, quite nice chapter on applications of these Taylor functions or Taylor polynomials. We're going to look at two main applications today, but first there's a little bit of a summary here of what we learned in the previous section. I won't go into this too much as obviously you've got these videos to go back and refer to, but reminder one here just summarizes for us what a Taylor series is. So we say that if we have some function f of x, then if indeed it is possible to represent that function as a power series, we can always write it like this. So this is an infinite series for us of the nth derivative of the function evaluated at this point a that our series is centered around, divided by n factorial multiplied by x minus a to the n. So that's our Taylor series format, exactly like we learnt in the previous lecture. And we remember, of course, that if we have the special case where a is equal to 0, that's what we call a Maclaurin series instead. So it's really just a simplification of the Taylor series, but it gets its own name. Out of interest for everyone, I don't, sorry if Brenda told you about this in the last lecture. If you don't know, Mr. Colin Maclaurin, who this is named after, was a famous mathematician from Scotland. And I learned today that he actually went to university when he was 11 years old and became a professor at the age of 19. He was the very youngest professor right through from the 1700s. He still remained the youngest professor ever to have been in existence until very recently, actually. In 2008, a young woman from the US became a professor at 18, but that's just amazing to me. Thought I would point that out as a little good factoid to know. But anyway, yeah, for our situation here, we just say that a Maclaurin series is this special case of a Taylor series where it's centered around the point a equal to 0. The other thing we learned in the previous section, 11.10, was this expression here, which we call Taylor's inequality. And this is what we use for finding the accuracy in using a Taylor series to kind of represent a function. And we kind of learnt about this last time and how we figure out what these m's and these constants d are. Kind of the two main things we have to figure out. But just to summarize again, what this is really telling us is if the n plus 1th derivative is bounded by m and we are within d, as in we're within d distance of our center point A. To kind of remind you, Brenda had these nice drawings this last time where if you think about the kind of timeline of x, x just kind of increasing like this, then this says that if we're centering our Taylor series around the point A, we essentially have to be within d distance of A. So somewhere in this region between A minus d and A plus d, all of these values of x here is where our Taylor series holds. Yes, so if we have our n plus 1th derivative bounded by our number m, our number m, and we are within d units or d distance of our center point A, then we can say that this inequality, what we call Taylor's inequality, holds, and that gives us, you can say that that's for the size of the remainder. So that lets us work out how accurate our Taylor approximation is at that point. So again, if for any reason you've missed that last video or you want a bit of a reminder of that, I'd kind of encourage you to go back and check that out before we carry on, because we're kind of going to be using these two facts throughout this section today. So the first the first application we're going to think about is approximating functions as polynomials. So this is really where thinking about that error kind of comes in. And you can imagine that there are many situations in which we want to take a function that's maybe quite difficult to work with. It might have some kind of tricky behavior, it might be difficult to differentiate or integrate, and we might want to approximate it with some of these nice, simple Taylor series polynomials instead. This really comes up an awful lot in all kinds of areas of applied math. There's almost an endless list. I couldn't say all of the applications, but essentially anywhere that we have some complicated function that we might want to work with a simple polynomial instead of that complicated function. So this comes up in physics applications like electric fields, thinking about water waves, lots of engineering-y type applications, thinking about the kinds of structures and how forces are going to interact. It comes up in finance when you're working out how to balance your portfolio. People use Taylor series to kind of approximate the behavior of your stocks over time. And last but not least, it also is essentially what a lot of calculators use. If you type in sine x or e to the x into your calculator, then really what it's doing is working out a really super accurate Taylor series with lots of terms for that quantity, for e to the x or for sine x, say. And that's actually like what it's calculating to give you a super accurate approximation to that quantity. So these really come up kind of all over the place, but enough of that from me. We'll get on to this question that we've got here. So here we're asked to take some function, f of x equals x to the 2 over 3, and to come up with a Taylor polynomial with degree 3 centered around the number a equal to 1. So we would like to imagine in this case that we're not able to work out ourselves what x to the 2 over 3 is. You can imagine if you didn't have a calculator, the cube root would be pretty tricky for a lot of numbers. And so we're going to try and come up with a Taylor polynomial for it to kind of simplify being able to work out what this function is equal to. So we're going to do that just like you did with Brenda in the last video. And as with all of these questions, I would first suggest doing yourself a little table to work out these values of the nth derivative. And in fact, here you can see that we're centering around a equals 1. So the quantity I'm going to be concerned with is the nth derivative evaluated at the point 1. And if I wanted to work out the actual infinite Taylor series for this function, you can imagine that I'd need to test all the way from n equals 0 up to infinity. But in our case, we're just asked to think about the Taylor polynomial at degree 3. So all I'm going to need is the 0, 1, 2, and 3 values of n here. So the 0th derivative of f of x is just f of x. So that's going to be x to the 2/3. I then want to take the first derivative, so differentiating x to the 2/3 to give me, I think, 2/3 x to the minus 1/3. I then differentiate it again to get the second derivative. I think that's going to give me, well, 2/3 times minus 1/3, or minus 2/9 x to the minus 4 over 3. And then when I differentiate it again, I think that's going to give me plus 8 over 27, so that's minus 2 times minus 4 on the top, and 9 times 3 on the bottom, multiplied by x to the minus 7 over 3. And now we can go through and fill in our final column of the table, just to summarize here that we're working on part A, where we essentially just need to substitute in x equals 1 to all of those derivatives that we've worked out. So we know that 1 to the power of 2 over 3 is 1. And the good thing I notice here actually is that when I substitute in 1, we know that 1 to any power is just still equal to 1. And essentially all of these x terms just give me 1. And so all I need is the fractions in each of these. So the first derivative of f evaluated at 1 is going to give me 2/3. The second derivative evaluated at 1 is going to give me minus 2/9. And the third derivative is going to give me just this 8 over 27. So just all the fractional parts there. And then, just to recall for a second, we remember that our formulae for the Taylor series is like we've got here. So not only do we need these nth derivatives, but we also need to be dividing through by n factorial and multiplying by x minus a to the power of n. So when I do that, I can go straight to writing out what my Taylor polynomials with degree 3, i.e. this t3 of x, is equal to. So first I need my f0 at 1 that's 1 as we said, divided by 0 factorial, which we know is 1, multiplied by, well, since a is 1, that would actually be multiplied here by x minus 1 to the 0, but we know that that is just 1, so the first term is 1. Carrying on, I need my first derivative of f evaluated at 1, that was my 2/3, divided by 1 factorial, which we know is just 1, and multiplied by x minus 1 to the 1. I'm then going to need my third term in my Taylor series. That's my, actually I don't want to plus there, that's my minus 2 over 9, taken from this table over here, the second derivative, multiplied by my x minus 1 squared, and divided by 2 factorial. And finally my third term, we said that that was given by 8 over 27, the value of the third derivative, multiplied by x minus 1 cubed, and divided by 3 factorial. So there we have it. Just like in the previous chapter, but just to kind of point it out in this kind of application to it, specifically approximating a function. This is a quantity here that we can approximate to our original f of x equals x to the 2 over 3. So there we have it, that's part A done, and we can move on to part B here, which is a little bit more technical and involved, I suppose. So here we're asked to use our Taylor inequality, just like we learned in the previous lecture, to estimate the accuracy of our approximation f of x roughly equal to the nth Taylor polynomial. And here we're specifically given the range that we should be looking at x between 0.8 and 1.2. So the first thing I can note is that this very much looks like kind of seems to follow on from the example I had in A. And this is because we can see here that my value for A, the centering point of the Taylor polynomial we just worked out, is in the center of this region. So it looks like indeed a Taylor series centered around A equals 1 is really what we're being asked about here. And although the question says some general Tnx, of course you can imagine that the accuracy of our approximation is going to be different depending on what n we pick. So here we're just going to think about this T3 just for example, because that's what we've already worked out, but you could actually do this for any n that you wanted to. So just to summarize a bit before we start, let's say if we knew x to the 2 over 3, then our accuracy, or essentially our remainder, Rnx, would be exactly equal to our nth Taylor series minus f of x. But obviously in these situations, if I want to approximate some function f of x with its Taylor series, generally that means I can't work out what the series itself, what the function itself's value is. So if I could work out x to the 2 over 3 to find the error here, then I wouldn't have needed a Taylor series after all. So we can just say, usually we don't like to use this idea of what f of x is to work out the remainder. But usually we can't work out f of x. So obviously you could in this situation because you all do have calculators or computers, but we just need to assume when we're working out these errors that we don't have that. And that's why we ask you specifically in these questions often to use Taylor's inequality to solve them. So, as I said, let's take n equal to 3 here, since that's the case we're already looking for. Since that's the case we already worked with in part A. So we know here from Taylor's inequality that our R3 of x, the remainder when I use a Taylor series of degree 3, is going to be less than or equal to sum m over 4 factorial multiplied by x minus 1 to the 4. So I take that from the definition of the inequality just up here with n equal to 3, and we know that this is going to hold we're going to need to have this hold for all x between 0.8 and 1.2. We're centering around 1 here, so i.e. We have d equal to 0.2 in this case. So that's how far away that we're ever going from our centering point of a equals 1. Kind of makes sense, right? We only go from 0.8 to 1.2. centered around 1, so we're only ever 0.2 away. And also taking the definition of Taylor's inequality, we know that this quantity m is going to need to be at least the absolute value of the fourth derivative of x for all x in that range. So let's start working out what all those components are. Essentially, all I need now is to work this out. I've got my x minus 1 to the 4. I can think about what values that's going to take in the range, but the main thing I need to work out is the value of this m here. And to do that, I'm obviously going to need my fourth derivative in order to work out this expression here. So I've already got the third derivative from my table, from part A. It's just as we wrote here. So I can take that and differentiate it once more to give me f4 of x equal to well, I need to take 8 over 27 and multiply it by minus 7 over 3. I think that gives me minus 56 over 81 times x to the minus 10 over 3. And I need to think, okay, now what's some m that bounds the absolute value of this function, this f4x? Well, the first thing I can note is that x is always going to be bigger than 0. Because we've said specifically, as here, that it's always between 0.8 and 1.2, so it's always going to be positive. I should write this a little bit differently because that looks kind of like a minus. Let's do a little 1. So x is greater than 0 here, and so one thing I can notice is that f4 of x is always going to be negative. This is because if x is some positive number and I take it to the power of minus 10 over 3, it's still going to be positive. So it's essentially I'm doing 1 over x to the 10 and then cube rooted, so that's still going to be a positive number. But then I multiply it through by minus 56 over 81, so my result is always going to be negative, because we know a positive times a negative is a negative. The second thing I notice here is that my f4 of x is an increasing function. So the bigger x I put in here, the bigger the answer is going to be. You can imagine, well, I guess at least for all values on this range, for 0.8. Actually, it wouldn't matter if it weren't outside of this range, but the bigger number I put in, the bigger number I'm going to get out of f4 of x. Therefore, we can say that the maximum must be at the biggest value of x that I'm ever going to put in. And we remember again that all x's I'm putting in are between 0.8 and 1.2. So I can say that the max must occur at that endpoint, that x equal to 1.2. I'm going to put a little bit of red text here and say that when you're doing these questions, you should always, and please remember to do this, let's call it, always check this and provide reasoning. Doesn't need to be a long essay, but not all derivatives that you work out are necessarily going to be increasing or decreasing functions. You also might have the maximum could be at some point in the middle. Let's say the maximum was at x equals 1. It's possible here. So it's always worth having a check. Do I have an increasing function? If yes, my maximum must be at the end. Do I have a decreasing function? If yes, my maximum must be at the beginning of the region. Or if it's neither, then you need to kind of convince yourself where that maximum value is. And just a little sentence of explanation will do it, or maybe even a sketch of the function if it's something you could sketch out. But it's always important just to show us there that you are kind of thinking about where this maximum is going to occur. So I can then sum up to try and come up with my final value of m here. So we know that m needs to be bigger than every single possible value of f4 of x in this region, right? We wrote that just here. And so it certainly needs to be bigger than the maximum value of that function, which we've said occurs when x is equal to 1.2. So therefore I can sum up and say that my value of m has to be at least what did we say? The absolute value of minus 56 over 81 times this 1.2 to the minus 10 over 3. And this is where my 0.1 that we wrote here comes in. So we said that we knew that this function is always negative for all x in our range. And so actually the value inside of our absolute value sign is going to be negative. And so when I take the absolute value, I can essentially just rub out these absolute value lines and rub out this negative in front of the 56 and say, okay, well, when I take that absolute value, I'm going to get the negative of what I had in the first place, and m must be at least 56 over 81 times 1.2 to the minus 10 over 3. So now we're almost there. So we almost have everything that we need to find out our value of R3x, the error when we use the third degree Taylor polynomial. So I know that the absolute value of my remainder, R3 of x, I can start to substitute my values in, must be less than or equal to my new value of m, which we've said is 56 over 81 times 1.2 to the minus 10 over 3, divided by 4 factorial, and multiplied by, well, before we just had an x minus 1 to the 4 here, but as we know, we're trying to find the kind of upper bound for this error, so what's the biggest our error could ever be, and so we need to consider the kind of maximum value that this x minus 1 to the 4 can take for our x between 0.8 and 1.2. And I believe that actually occurs at either of these two endpoints due to the absolute value here. So 0.8 minus 1, taking the absolute value, is the same as 1.2 minus 1 when you take the absolute value. So actually I can pick either endpoint. So let's just write that down here. If I take 0.8 minus 1 to the 4, oh, actually, sorry, I've been forgetting to put my absolute values in here. You can see in the equation we had these absolute values around this section, right? So actually I should have had absolute value signs up here and also here. So I can take either endpoint to get my maximum, and that's going to give me, with the absolute value, 0.2 to the power of 4. And there we have it. If I were to work out what this sum would be, this 56 over 81 times 1.2 to the minus 10 over 3 divided by 4 factorial times 0.2 to the 4. Of course, you'd need a calculator to work this out. If you did it, I think you'd get, if I've done it correctly, 0.000251. However, if you were doing this in an exam, of course, we'd accept the answer like this, but I just wanted to kind of show you what our error is, and that tells us that if I'm using the third degree Taylor polynomial, then my accuracy, my biggest error possible, my error has to be strictly less than this number, this 0.000251. So that's how close I am to the truth when I use this third degree. The higher a degree you use, the closer an approximation you're going to get by the theory of the Taylor series. But here we can see that our accuracy is already pretty good. If you were using this to build a bridge or something, maybe you'd want to do a higher degree Taylor series. When you're doing these things in practice, it's always kind of a bit of a trade-off, like how accurate do I need my result to be given the setting that I'm in? You know, am I building a bridge or am I just doing some kind of exploratory analysis, versus kind of how much time and effort you want to put into the calculation. So there's that kind of pull and push there that determines in reality what degree we'd want to use. So to continue on to our final example, here we think about using Taylor polynomials and Taylor series to do approximate integration. So we've already done various different approaches for approximate integration. We saw these in one of the previous sections, but this is actually going to provide an alternative for those. So I'll say here, this can be an alternative for any of our approximate integration techniques that we learned. So it can be an alternative for our trapezoid rule, or our midpoint rule, or our Simpson's rule. If we didn't want to do any of those, then we could use Taylor series actually to work out the areas under curves. So essentially what we're asked to do here is to take this curve, y equals sine x over x, and approximate the area under it for over some range of x using Taylor series. So again, we could use our trapezoid or any of our rules here, but instead you can imagine what I could do is approximate this function, the function we care about, with a Taylor series and integrate that Taylor series instead. So just to summarize, what we really want here, what we're asked to find, is the integral between minus pi and pi, we're given here, of sine x over x dx. But we're going to assume that for some reason we can't work this out. Maybe you didn't know the integration by parts, or maybe when you work this out it just ends up being something awful. And so you can imagine that what I could do instead would be to replace this function with a Taylor series instead. Now we know that Taylor series have these nice polynomial forms, right? They're really just constants multiplied by like x cubed and x to the, x to the 4, x to the 5. And so they're always really nice and easy to integrate. So rather than doing some complicated integral, I get to do a much nicer one instead. And really the applications here are any of the same applications that we had in our numerical integration chapter. So any of the situations in which you'd want to use a trapezoid rule, you could do this as an alternative instead. So let's just sketch out just for a second this function that we're asked to think about here. So if you'll believe me, and you could check on Wolfram or something instead if you wanted, I think that the function y equals sine x over x looks a little bit like this. And in particular, we're asked to think about it between minus pi and pi. Do that a bit more neatly, which are given by these points of intersection with the x-axis here. And we're asked to find the area under it, which we know is given by this little area here. One thing you might want to note, and I think this we'll talk about why this is in a minute, is that this value, the value of this function when x is equal to 0, is actually 1. That seems a little bit weird because you've got to divide by 0 here in the function, but we'll see in a second why that's true. And hopefully you'll kind of be convinced that I'm right here. So the first thing, we want to try and figure out what our appropriate Taylor series is going to be here. The first thing I want to think about is what should A be? So where should we be centering our Taylor series around? And one thing we know about Taylor series is that if it's centered around some point, then probably the middle of the area of integration is going to be a sensible place to go. So I'm going to choose here my A equal to 0. I'm going to center my Taylor series around the point 0, since this is in the middle of the region that I want to think about. So this is because we're asked to integrate between minus pi and pi. So A equals 0. We've got the middle of that region. We know that Taylor series hold in some area like plus and minus d around the centering point. So it kind of makes sense to choose that middle so that we have the kind of the same distance away on either side, plus and minus. So now what I need to do is figure out what my Taylor series is, right? What do I substitute in there for sine x over x? And to do this, just like before, I'm going to do one of our nice Taylor series kind of tables where we consider, for different values of n, what is the nth derivative? And you might want to leave yourself a little bit extra space here as a warning. And then lastly, what is the nth derivative at our center point? So in that case here, we said we had A equal to 0. Before I work out how many values to put in my table, the next thing I need to care about is what degree Taylor series am I going to do? And in this question, we're not specifically told it, right? We're not told to do the second or the third or the fourth degree Taylor series. In an exam question on this, we'd often give you that degree just to be honest, to make things easier to mark and to assume that everyone's to get everyone doing the same amount of work. But you can imagine in real life, if you were doing one of these questions, again, you might not know the best degree to do it to. So then it would be, like I said before, this kind of trade-off of accuracy versus effort. For argument's sake, in this question, we're going to choose n equals 2. and do ourselves the second degree Taylor polynomial. This will hopefully get us a good idea of how to answer this question without doing too much extra algebra. We'll see in a second that this is going to get a little bit messy. So that's why I don't want to do it too much further than n equals 2. So this means that I'm going to just need to test out 3 values of n. That's going to be 0, 1, and 2. So the 0th derivative, i.e. just f of x really in this case, we've said is given by sine x over x. And you can start to see why this is a little bit messy, because I'm going to need to use the quotient rule to differentiate this. That's going to give me what's it going to be? X cos x minus sine x all over x squared. First, the top times the differential, sorry, the bottom times the derivative of the top minus the top times the differential of the bottom divided by the bottom squared. And I'm then going to need to differentiate that again to get the second derivative. And this is why I don't want to go further than n equals 2. You could do this in your own time if you wanted to, but maybe you'll all believe me that when you differentiate this again, you're going to get x squared minus 2 times sine x plus 2 times x times cos x all over x cubed. So I haven't written out the full details there, but essentially if I do the quotient rule on my first derivative, that's kind of what comes out at the end once you collect the terms back up. Then I need to think about, well, what's going to happen here when I substitute when I substitute x into 0 equals 0 into each of these terms. So the first one here, let's draw myself a little arrow down here. I'm asked to think about here the limit as x tends to 0 of sine x over x. And this kind of ties back to that point I spoke about here on the diagram, the fact that we have x equal to 1 at that point. To convince yourself of why this is equal to 1, you could use L'Hopital's rule here. So we see that we have ourselves a 0 over 0 limit here. Sine of 0 is 0. If x is 0, so we have a 0 over 0 case. But if I use L'Hopital's rule and differentiate the top and the bottom, that's going to give me cos x over 1. Oh, sorry, I forgot the limit. It's going to give me the limit as x tends to 0 of cos x over 1, which we know is equal to 1, because cos of 0 is indeed 1. So we can convince ourselves that fn of 0, f0 of 0, the 0th derivative should be equal to 1. So now we need to think about our first derivative of f, and to do that we can see that we're going to need some similar steps. So here I'm thinking about the limit as x tends to 0 of this x cos x minus sine x over x squared. I'm thinking of this as a limit because you can see that when I put in x equals 0, I get myself a 0 over 0 kind of limit, right? So my top's going to tend to 0 because x is 0 and because sine x is 0. And the bottom's going to tend to 0 also because we have a 0 squared there. So I need to use L'Hopital's rule once again. And that's going to give me, I believe, the limit as x tends to 0 of, when I differentiate this, I'm going to need to use the product rule here. It's going to give me cos x plus x times sine x minus cos x over the derivative of the bottom, which is 2x. So I can see that gives me my causes cancelling out, and I'm just left with the limit of x sine x over 2x. The x's cancel, and we just get the limit as sine 0, which itself is 0. Where's my pen not working? There we go. So I can substitute in 0 as my first derivative, and hopefully you can all see now why I didn't want to, again, why I didn't want to do a higher degree than 2 here. We could also take similar steps to work out the value of our second derivative at x equals 0. I'm going to leave this for you guys to do yourselves if you want, and hopefully you'll believe me that we get minus 1/3 out when we do these kind of L'Hopital steps many times. Okay, so we're almost there, at least figuring out what our Taylor series is. So what do we want? get rid of that. There we go. So we can say that sine x over x, our original function, is approximately equal to the second degree Taylor series around the point a equals to 0. And to work out what that is, I just need to substitute in all of these values I just calculated for my nth derivatives with that kind of the factorial and the x minus a to the power of n. So what does that give me? Well, I'm going to get a 1 divided by 0 factorial times x to the 0, so just 1. I noticed that the coefficient of my x to the 1 term is going to be 0, so that term's just going to disappear. And then the only other thing I need to add is my degree 2 term, which we've said is going to be equal to minus 1/3, the second derivative evaluated at 0, divided by 2 factorial and multiplied by x minus 0, because I'm centered around 0, squared. And you can see that if I expand that out, that's the same as 1 minus x squared over 6. Nice and simple. So it seems kind of strange, but what we found here is that sine x over x is at least pretty similar to the function 1 minus x squared over 6. But we're not quite there to the very end answer, right? Because we weren't just asked to find the Taylor series in this in this question. We were asked to approximate the area under this curve. So I wanted to find the integral between minus pi and pi. Let's write this out. What I wanted was the integral between minus pi and pi of sine x over x dx. But we said that, for some reason we can't work that out. We don't want to do it. But now what I can say is that integral must be approximately equal to the same integral, minus pi and pi, but of this Taylor series, of this 1 minus x squared over 6 dx. So I just replaced my original function that I don't know how to integrate with my new Taylor series, which I do know how to integrate, right? It's just a nice, simple polynomial expression. So when I integrate that, what am I going to get? I get, 1 integrates to x, minus x cubed over 6, minus x squared over 6 integrates to minus x cubed over, 3 times 6, so 18. And we know that we want that between minus pi and pi. And I can just go through and substitute those pi's in. That is going to give me pi minus pi cubed over 18 minus, let's get this right, minus pi minus pi cubed all over 18. Try and simplify down those lots of those kind of double negatives without making any mistakes. So you can see here that this second pi here, we end up with it being positive, so actually have 2 pi in there from the first term and the third term. And we also have, what would that be, 3 negatives on the final term here in our expression, making that also negative. So I'm going to have minus 2 pi cubed over 18 as my answer, or equivalently with a little bit of simplification, 2 pi minus pi cubed over 9. And there we have it as our final answer. Just to recap a little bit, we were asked to approximate the area under this curve, y equals sine x over x, using a Taylor series. And we did that by replacing our function sine x over x with a Taylor series. We chose the order, the degree of the Taylor series that we were going to use to be n equal to 2, so that we didn't have to kind of calculate too many of these complicated expressions. And when we substituted that Taylor series into the integral, like just here, we found that our approximation to our integral is this 2 pi minus pi cubed over 9. And just to give you a little visual kind of exploration of what this was doing, you can imagine that if I were to go back to our original plot of this area, so we said that we were integrating under a region that looked a little bit like this, between minus pi and pi. And what we were looking for was this area underneath the curve during that region. Now, different degrees of Taylor series is essentially approximating this curve with different polynomial powered expressions. So if we only took the Taylor series here up to degree 1, then I would have just been approximating this curve with a straight line, a flat line with no power of x, so that would have just been, in this situation, that line across here. As it was, we used a quadratic expression, this 1 minus x squared over 6, to approximate this curve and therefore the area underneath it. And indeed, if you plotted out this 1 minus x squared over 6, I believe that gives you a curve that looks a little bit like this underneath our sine x over x, which we can see in this case was actually a pretty good approximation to this curve. And I believe if you worked out the difference between this value that we got, this 2 pi minus pi cubed over 9, and the real value of the integral of sine x over x, I think you'll find that there's not too much difference. We could have improved our approximation by using a higher order Taylor polynomial. For example, if we'd used the T4, so the 4th degree Taylor polynomial, we would have got a quartic line instead of a quadratic line to approximate this function. I think you could look this up on Wolfram if you want to. It does Taylor series pretty well. That would have ended up with a curve which even closer fit our sine x over x, and that would have given us a closer approximation to the area. But as I kind of mentioned before, it's this kind of trade-off between how many more terms do I want to have to calculate for the extra big kind of accuracy that I'm getting in my approximation. So yeah, that's it for this chapter, and indeed for the lectures for the course. We will be back with a review lecture for you all, but this is kind of the end of the content for us. So yeah, thanks so much to everyone for being patient and understanding as we transition to these online lectures, and I hope that they've been helpful. And don't forget to keep using the discussion boards in the calculus workshop if you have any questions. But otherwise, from me, best of luck on the final exam.